Let me introduce, now let me introduce Ryan. And most of you know, I'll mention a few things that you might not know. He's very modest, so I needed to really work to get this out of him. He graduated from Rutgers, which I think is basically the University of New Jersey. And that was in 2020, and he showed up during COVID, and I met him a couple of years after he showed up. And he got an MS, says an MS, already obviously in Michigan. And he's also getting an MS in robotics, which is this department, and obviously the PhD in Aerospace. And as you're going to find out, his research is focusing on identification, but specifically online identification. And when he got here, I asked him to work on RLS because I think RLS is a really neat kind of algorithm. That was what we call understudy. It really showed how much underappreciated and underdeveloped RLS was. In 2021, he did an internship with the Air Force, but I think you were here. You didn't actually go there. Yeah, that was a COVID times, probably nostalgic. Oh, he did an internship at Reliable Robotics. And and also very important, all of his PhD was paid for by NSF because he's been on an NSF fellowship, which is amazing. Anyways, this is what we're going to do. Ryan is going to speak maybe around 15 minutes, 60 if he really needs it. And if there are any quick clarification questions, yeah, you can ask, but they need to be quick questions and quick answers. Anything that's really detailed or involved, we'll do that when he's done talking. And if he says anything that you might want to ask about, you might want to take notes because I asked him to number his slides. And then you could just say, oh, Brian, can you go back to slide 20? I have a question. And then he'll be able to find whatever the slide is relating to your question. And then anybody in the audience is welcome to ask some questions. And when you completely run out of questions, we'll ask the audience to step out, and then the committee will ask them additional questions. And when those questions are, we'll ask Brian to step out, and then we'll have our meeting and make our decision. And without any further ado, Brian.
Awesome. Thank you so much for the introduction. Hi, everyone. My name is Brian, and today I'll be presenting my dissertation on theories, extension, and applications of recursive least squares. So first, a little bit of motivation. Control systems are designed to be robust to various conditions. Let's say your autopilot on your aircraft is designed to handle many different conditions. A driving car is intended to take care of various conditions on the road. And these control systems work under lots of nominal conditions. But what if something happens to your system? Let's take this example where we have an aircraft and all of a sudden the wing falls off and your aircraft is performing very differently than normal. Or for example, you have a helicopter that's picking up cargo. You may not know exactly how heavy this cargo is, how it will affect the aerodynamics of your aircraft, and maybe your system is performing differently than usual. So adaptive control is a strategy in which we adapt our control based on the current conditions using data that we're collecting. The method I'll be focused on is called indirect adaptive control, which is primarily composed of two parts. The first is learning dynamics online from data. And this learned model will be informed by how the system is currently behaving. And the second is to adapt our controller using our learned model. This dissertation focuses on online identification for learning dynamics online using recursive least squares. When it comes to learning system dynamics, you need to excite your system to learn the dynamics. Think about like a car that you've never driven before. You want to know how it handles a turn. You're going to have to take a turn in that car. Or say you have an aircraft and you want to know how it performs in a climb. You have to take a climb because instead of modeling through first principles or physics-based, we're learning our dynamics entirely from data here. However, this comes at a cost, which is that we're doing two things simultaneously, both tracking and learning dynamics. So if our controller is working really well, then good tracking will actually cause loss of excitation. Consider like this ball and beam example. You have this ball and beam, and when it's in its transient, getting to the position it should be in, we have a lot of excitation, a lot of ability to identify our system. However, once it's in steady state, there's very little excitation left. There's not a lot of information to identify the dynamics of the system. So the first motivating question for this presentation will be, how can we identify time-varying parameters when we have different levels of excitation? So this presentation will be split into 3 parts. First, an introduction on recursive least squares and addressing this problem of high and low excitation. The second is introducing a new idea called directional excitation and how this applies to input-output modeling for modeling dynamics of systems. And finally, we'll talk about unifying different RLS algorithms from the literature and some connections to the Kalman filter. So first, part 1 and an introduction to recursive least squares. This is kind of like a mathematical introduction to RLS. RLS you can derive in one of 2 ways. The first is through a cost function, in which we minimize the least squares cost function with a regularization term, and we compute its minimizer at each step. Another way is a stochastic setup, in which we have identity dynamics, theta k plus 1 is theta k, and some linear measurement process. And we find the optimal update at each step. And the results for either of these setups is a set of update equations. The first is RK, which is our inverse covariance, and theta k, which is the mean of our estimate. And then we can also use matrix inversion lemma to update PK, which is our covariance, directly. The reason we do this is because updating RK is pretty high computational cost. We need to invert this n by n matrix. So that gives us n cubed complexity. Whereas with matrix inversion lemma, we can directly update PK, and that only costs us Pn squared complexity. And as we'll see in the next slide, RLS is really great for estimating constant parameters for example, the transfer function of some unchanging dynamics. So here's kind of what that looks like in practice. RLS is propagating some Gaussian belief of parameters. Let's say we had 2 true parameters, 1 and 2 here. And we can see that as we collect more data, we both become more confident in our estimate, and the mean of our estimate becomes closer to the true parameters. And while this is really nice in 2 dimensions, visualizing it like this is kind of intractable in higher dimensions if we wanted to estimate more than 2 parameters. So what we want are some kind of key metrics that tell us how our algorithm is performing in higher dimensions. And one way we can do this is first by considering the ellipse with Mahalanobis distance 1. And Mahalanobis distance is kind of like the multivariable version of standard deviation. So when you're 1 standard deviation away from your mean, the mean is given by theta k, and the lengths of the principal axes of our ellipse are the square root of the eigenvalues of the covariance. Which means that if we look at theta k and pk, theta k gives us the mean of our belief, and the eigenvalues of pk show us the confidence of our estimate in different directions. So what happens when we identify time-varying parameters instead of constant parameters? Here's an example where we have 4 parameters. The first 2 are constant, and then the last 2 are time-varying. And if we use classical RLS, we run into this kind of problem where the eigenvalues of PK keep decreasing. We only become more confident in our estimate. And as a result, eventually we can't keep up with these time-varying parameters. So theta 1 and theta 2 identify really well, but theta 3, theta 4 eventually are unable to track. So how can we adjust RLS to identify time-varying parameters? One classical way we can do this is called RLS with exponential forgetting. And the standard setup for this is you introduce a forgetting factor lambda, which is between 0 and 1. And this puts higher weight on more recent data, exponentially higher weight on more recent data. And the results are some update equations that look very similar to RLS. The only difference here is that we're multiplying RK by lambda at each time step, which allows us to be less confident in our estimate. Here's that same example where we have 2 time-varying parameters and 2 constant parameters. And from 0 to 400, you can see we're performing really well. We're tracking both the constant parameters and the time-varying parameters. And this is because our signal-to-noise ratio is really high. So we have a lot of information to identify our parameters. But from 400 to 800, we decrease the signal-to-noise ratio by a large factor. And all of a sudden, our estimate is really bad. So you can see in our eigenvalues, we have very little confidence in our parameters, and our estimates are all over the place. We become really sensitive to noise. And this is kind of the phenomenon called covariance windup. So if you don't have a lot of data, the term for this is like persistent excitation. If you don't have good data constantly coming in, your covariance becomes really large and you become really sensitive to noise. So the first thing that I'd like to present is a new extension of RLS called Exponential and Cyclic Resetting RLS, which is a method to help prevent covariance windup. So we'll start with an interpretation of exponential forgetting. In the exponential forgetting update equations, at each step, we're multiplying RK by lambda. Maybe another way we can look at this is we're subtracting something from RK, which is proportional to the distance from RK and 0. So RK is getting closer and closer to 0. But what if instead of getting closer to 0, we got closer to some non-zero matrix? So the idea here is to replace 0 with some positive definite matrix R infinity. And that gives us these new update equations for RK. And we use the same theta update equations as regular RLS. And this gives us some really nice properties. The first of which are guaranteed lower bounds and upper bounds on the covariance. So we can't become too confident, and we also can't become too uncertain. And the next is a resetting property, which is if you have very little data coming in for a long amount of time, we'll reset to kind of like a baseline level of uncertainty. So what does this look like? Let's again go to that problem where we have 2 constant parameters and 2 time-varying parameters. From 0 to 500 and 1000 to 1500, we have very good signal-to-noise ratio, persistent excitation. And then from 500 to 1000, we lose persistent excitation. So our signal-to-noise ratio is much lower. And we have a constant forgetting factor, and R infinity will set to identity. And what happens in classical exponential forgetting is what we saw before. Our covariance becomes really large and we become really sensitive to noise. And you can see our estimate of theta 3 is all over the place. However, with exponential resetting, we limit our uncertainty. So we limit how big our covariance can become. And as a result, between 500 and 1000, even though we're not tracking theta 3 because we don't really have data to do it, we're not really sensitive to noise. We are only perturbing our belief a little bit. However, exponential resetting does come at a cost, which is higher computational complexity. So while RLS is usually done in theta, big O of p n squared complexity per step, exponential resetting, you need to take this n cubed cost to invert your R matrix. And the reason this is because at each step, you're adding this 1 minus lambda R infinity, which is already rank n. So there's no way to use matrix inversion lemma in this instance to reduce computational complexity. So the next question is, how can we modify this algorithm to maintain the original complexity of RLS? And this is a trick I'm calling cyclic resetting RLS. And this involves a few steps, the first of which is we diagonalize our R infinity matrix. And we can write it as the sum of n rank 1 matrices. Next, we can take a new RK update equation in which instead of adding a rank n matrix at each step, we're only adding this rank 1 matrix at each step with this coefficient that's kind of complicated but needed to make everything work out nicely. You'll notice that every n steps, we're adding 1 minus lambda to the n R infinity, which is that rank n matrix that we wanted. And using this trick, we can use matrix inversion lemma to update RK, to update PK directly in the big O of p plus 1 n squared complexity. So that gives us back to the original complexity of RLS. And this also has some really nice properties. So we have a similar guaranteed lower bound and upper bound on our covariance. And we have what I call like a cyclic resetting property, which is that instead of converging back to baseline every step, we're converging back to baseline every n steps. And between those n steps, we're kind of cycling between lambda to the power n minus 1 and 1 over lambda to the n minus 1. Okay, so what does this look like in practice? Same example again, and now cyclic resetting is here in yellow. So cyclic resetting, we have the same computational cost as classical RLS, but instead of our covariance eigenvalues being bounded at 1, they kind of oscillate a little bit above 1 and a little bit below 1. But overall, the performance is very similar to exponential resetting with the same computational cost. And we have the same performance in theta 3, where when excitation is lost, we have very little change in our beliefs. Okay, so that's part 1. Now for part 2, I want to introduce this new idea called directional excitation. And we'll go into some input-output modeling of dynamics afterwards. So let's consider the following example. Here we'll have 2 time-varying parameters, and ideally we want to track both. And we take some measurements with noise at each step. However, our regressor here, phi, is designed in such a way that the first term is really large and the second term is very small. So we have a lot of excitation to identify the first parameter, but very little excitation to identify the second parameter. Okay, so let's look at our 2 classical algorithms. Red is no forgetting and yellow is exponential forgetting. If we do no forgetting, we can't track the first time varying parameter, and we can't track the second time varying parameter because everything's converging. If we use exponential forgetting, we can track the first parameter, but our estimate of the second parameter is really noisy because we have little excitation. So ideally what we want is some algorithm that can identify the first parameter, first time varying parameter, with little change in the belief of the second parameter. So a little terminology is I'm calling the 1,0 subspace the excited subspace because it has high signal to noise ratio, and the 0,1 subspace I'm calling the unexcited subspace because it has very small signal to noise ratio. So a question is how would this occur in practice? Like when would directional excitation really happen? So for that, we're going to talk about input-output modeling of dynamics. So this is kind of the model structure we use in our adaptive control group for identifying online dynamics. Let's consider our true plant in discrete time. Yk is given by this input-output model, which is a linear combination of previous y's and previous u's. And we have some identified model of similar structure, but potentially different model order. And we can use RLS to identify this model using the following structure. So our phi, our regressor, is defined as a bunch of previous y's and previous u's. And the thetas are the coefficients of our input-output model. And using RLS, we can recursively compute what are the parameters in our input-output model. Here are kind of 2 examples that we're using this in practice. The first is like a quadcopter example, where we're doing adaptive control to improve tracking of a quadcopter. Here's a second example in which we're using adaptive control to do some reference tracking of altitude and airspeed on a fixed-wing aircraft. And you'll notice that like in these use cases, ultimately we want to track something. So the data going into our identification step will have like some kind of special structure. It might be sinusoidal in the first case, or it might be like a step response in the second case, for instance. So what happens when we're tracking well? Let's look at steady state tracking of a step response first. So we're identifying this input-output model. Suppose in the center here that our input converges to some value and our output converges to the DC gain times that value. So we're tracking this step response really well. What happens to our excitation? What happens is that we're only exciting a subspace of dimension 1. And it so happens to be the range of this matrix, G of 1 with a bunch of 1s and bunch of 1s below that. In other words, we're only exciting one particular direction, and all of the rest have no information about how the system is performing. Here's another example. If we're tracking a sinusoid in steady state, so in the center here, we have M is our gain, and then capital gamma is our phase. So if our input is some sinusoid, then our output will be some sinusoid multiplied by that gain and phase. In this example, we're only exciting a subspace of dimension 2. So we're only learning parameters in 2 directions here. And another thing to point out is that these subspaces are functions of the true plant. So like the gain and the phase are functions of the true plant. So in other words, we can't know ahead of time which directions we're exciting because we don't know the true plant. Here's another example. So now let's consider a different scenario. Suppose our model order was higher than our plant order. So for example, we have a 4th order true system, but we're over modeling it. We have a 12th order identified model. And we do, say, identify the model with RLS with no forgetting. Here's an example of the eigenvalues and the poles and zeros in our identified model. You see that we get the true model pretty well, but we have a bunch of pole zero cancellations. And we also notice that some of our eigenvalues aren't decreasing, so we're not becoming more confident in certain directions. And what this ultimately means is that we're not exciting all directions. And this kind of corresponds to our pole zero cancellations. They can be anywhere. It doesn't really matter where they are. So in this example, if our model order is higher than our plant order, we have some explicit expression for the excited subspace, but ultimately we're exciting the subspace and it has dimension at most n hat plus n. So in other words, there's n hat minus n directions that are completely unexcited that we know nothing about. So in summary, we're directionally exciting if we're tracking a step response or a sinusoid, if our model order was larger than our plant order, and this subspace depends on the true plant, which we don't know ahead of time. So how can we forget only in the excited subspace, but not in the unexcited subspace with no knowledge ahead of time of which directions are excited? So this is the second algorithm I'd like to present, which is called Subspace of Information Forgetting RLS, or SIFt RLS. So SIFt starts with a decomposition of a positive definite matrix. So positive definite matrix A, and we have some subspace S with a basis V. So you have M vectors V1 through Vm, and the range of V forms a basis for subspace S. And in this decomposition, we take A as the decomposition of the sum of 2 matrices, A parallel to S and A perpendicular to S, where A parallel to S has this form here, AV, V transpose AV, inverse V transpose A. And A perpendicular to S is A minus A parallel to S. So these matrices have some really nice properties. It's the unique decomposition such that A parallel and A perpendicular are both positive semi-definite. The rank of A parallel is M, which is the dimension of our subspace. The rank of A perpendicular is N minus M. And for all elements in for all elements in S, A parallel times X is the same as AX, and A perpendicular times X is equal to 0. So using this matrix decomposition, we developed the SIFt algorithm, which involves 3 steps. The first of which is called information filtering, in which we have some tuning parameter epsilon, and we use this tuning parameter to get rid of small singular values of our regressor phi. And we do this by taking a SVD of phi, and then we take any singular values that are too small and we truncate them. So in other words, we are taking the first QK columns of U where we have QK singular values that are bigger than square root epsilon. After filtering, we now forget only in the directions which are excited. So we do this as follows. We have our R matrix, which we decompose into R parallel and R perpendicular, and we multiply only R parallel by lambda. So we only decrease the value of R parallel. And that gives us the following update equations. And then we can also use matrix inversion lemma to directly compute the inverse, PK. And finally, we take our update step, which is the same as classical RLS. We're adding our phi k transpose phi k back and using the same theta update. And the nice thing about SIFt is that it's designed in a way that keeps the same computational complexity as classical RLS. SIFt also has some really nice properties. The first is a guaranteed upper bound and a guaranteed lower bound. So I want to kind of make a parallel between exponential forgetting and SIFt. So if you look at exponential forgetting and you impose this really strong persistent excitation condition, which is that we're persistently exciting with a window of 1. So at every step, we're exciting every direction. Then we would get the same kind of bound that we're getting in SIFt. So you see 1 minus lambda over epsilon, and we have 1 minus lambda over alpha. And kind of the way I like to think about this is in exponential forgetting under this really strong condition, we're exciting and forgetting in all directions, whereas in SIFt, we are exciting in whatever direction and forgetting only in that direction. And in this way, we kind of get the same bound. So here's an example of how SIFt works. Say we had 4 time-varying parameters, and we're also going to look at 2 more parameters, theta parallel and theta perpendicular, which are in kind of arbitrary directions, but they're perpendicular to each other. We take some measurements at each step, and we're exciting in kind of this funny way. So between 0 and 400, we're exciting the first 2 parameters. Between 400 and 800, we're exciting the 3rd and 4th parameter. And then 800 to 1200, we're exciting only theta parallel. So let's see what happens in practice here. So from 0 to 400, we are exciting theta 1 and theta 2. And so we can track these time varying theta 1 and theta 2. But we don't change our belief of theta 3 and theta 4 because there's very little information in that direction. Then from 400 to 800, we're tracking theta 3 and theta 4, but we have little change in our belief of theta 1 and theta 2. And finally, from 800 to 1200, we're changing our belief of theta parallel, but since that's the only direction being excited, we have very little change in our belief of any other parameters. And in this way, we're able to track time-varying parameters that are excited while not changing our belief of other parameters which are not excited. Okay, that leads me to part 3. So in parts 1 and 2, I introduced 2 new extensions of RLS, but there are many other extensions of RLS in the literature, all for their own purposes. So a question I wanted to answer is, how can we unify all these different algorithms under one framework? And we'll see that there are also some really interesting connections to the Kalman filter. So yeah, as I mentioned, there's tons and tons of forgetting algorithms. And the kind of like formula for creating RLS extensions is some modification of the covariance update. So you have the same like theta update, but you change your covariance update in some way for your purpose. So there's like constant forgetting factor, there's a variable rate forgetting factor where lambda is time varying. You can do like covariance resetting, lots and lots of different algorithms. So here's the framework that I came up with to unify these algorithms. This is something I called generalized forgetting recursively squares. So this is set up using a cost function that has 3 terms. The first is the loss term, the second is the forgetting term, and the third is the regularization term. You'll notice that the loss term and the regularization term are the same as standard RLS. But the new one is this forgetting term, and it's a little weird in kind of 2 ways. The first of which is that it's negative, and the second of which it's theta hat, which is like the function we're optimizing over, minus previous thetas. And since it's negative, that means that we're encouraging theta to be different from previous thetas. So using this term, we want theta to be different from previous thetas. We can take the minimizer at each step, which gives us the following update equations. And what this looks like is we're subtracting f, which is the weight of our forgetting term, from pk inverse at each step. And using this formulation, we can put a lot of different forgetting algorithms under this same framework. So here are a bunch from the literature. And you can see that if we choose different values of fk, so the weighting for our forgetting term, then we get all of these different algorithms from the literature, starting from generalized forgetting. So that's shown in red, is our different choices of fk. And then also shown in black are how these different algorithms relate to each other. Okay, and so a big part of this work was putting the different algorithms under the same framework to study stability and robustness. So first, stability, we have our update equations, and we're going to assume that we have measurements with no noise here. And that lets us get the following aerodynamics, where theta k tilde is the error between our estimated parameters and the true parameters. And we have the following conditions. So A1 through A4, the first is that our forgetting is positive semi-definite. In other words, we want theta to be different from previous thetas, not like more similar to previous thetas. The second is kind of similar to an upper bound on the covariance. You'll notice there's this like double inverse. You have pk inverse minus fk all inversed. So it's kind of like pk, slightly different. So kind of like an upper bound. And the A3 is a lower bound on pk. And finally, A4 is that our regressors weighted by our weighting matrix is persistently exciting and bounded. And using these conditions, we get really nice stability guarantees. So if we have A1 and A2, we're Lyapunov stable. A1, A2, A3, we're uniformly Lyapunov stable. 1, 2, and 4, we're globally asymptotically stable. And if we have all of them, then we're globally, uniformly, exponentially stable. The next are guarantees on robustness. So here we add a little bit of leeway to our assumptions. The first is that our true parameters are no longer constant. They could potentially be time varying. So we have our true parameters at step k plus 1 are our true parameters at step k plus some offset calling delta theta. And then in our measurements, we have potentially noise in both the measurement and the regressor. So I'm calling that delta yk and delta phi k. And that gives us some slightly more complicated aerodynamics. One thing you might notice here is there's a one-step delay between theta k minus theta true k minus 1. And that's like kind of the way it's set up. You only, your index is one ahead than all the data you've been using. And now we have a bunch more conditions. So A1 through A4 are all the same. And A5 through A8 are basically saying that all our disturbances are bounded. So the first is that our true parameters can't change too quickly. A6 is saying that our measurement noise is bounded. A7 is saying that our regressor noise is bounded. And A8 is saying that our true parameters are themselves bounded, so they can't become arbitrarily large. And using all these conditions, we get that our error is globally, uniformly, ultimately bounded by epsilon, where epsilon is this very complicated expression. So epsilon is like a bunch of terms. And ultimately, even though this is really complicated, it gives us some guarantee of robustness, that our error doesn't become too large. So in summary, we're unifying different algorithms from the literature. We have stability and robustness guarantees. And I think here's the cool takeaway from generalized forgetting is that A1 through A3 are in some sense providing design guidelines on how to design RLS algorithms. So if you notice that in these A1 through A3, these conditions are entirely functions of algorithm design. They have nothing to do with the data being collected or like if you're persistently exciting. They're entirely how you design the algorithm. So if you design your algorithm such that your forgetting is like in the right direction, you want to be dissimilar to old stuff. If you design your algorithm to have an upper bound on your covariance and you design your algorithm to have a lower bound on your covariance, you'll have some kind of guarantees of stability and robustness. So next, let's see how this relates to the Kalman filter, and we'll be using this for adaptive Kalman filtering. So first, we're just introducing some notation on the Kalman filter. This is standard notation, but I want to just make sure we're all using the same notation here. So we have our states X and our measurements Y. The one thing I'll like to point out is that I'm using capital sigma for process noise covariance and capital gamma for measurement noise covariance. And we have the following Kalman filter update equations. If these look different than usual, these are like the one-step version, where sometimes you present them as like a two-step version. And ultimately, the Kalman filter is derived from a stochastic model and has a stochastic derivation. RLS, on the other hand, is often derived from a cost function, which is completely deterministic. However, RLS is in fact a special case of the Kalman filter. It's a very special case which has identity dynamics. So A is identity. No inputs, B is 0. And it has no process noise covariance. So sigma is 0. And also you'll notice that the measurement noise covariance is the inverse of the weighting matrix. So the inverse of the weight in our RLS cost function. So since RLS is a special case of the Kalman filter, a natural question is, are other extensions of RLS also special cases of the Kalman filter? And through this, we'll show that yes, they in fact are. So to do so, we're going to do in two parts. First is a least squares derivation of the Kalman filter, and then we'll show how these extensions are in fact special cases of the Kalman filter. First, we're going to do a cost function derivation of the Kalman filter. We're introducing this notation of a state transition function. If we assume that our A is non-singular, then we can run our dynamics either in forward or reverse. And so we can create this T function, which transitions our state from step I either forward or backwards to step K. And now we can present the Kalman filter least squares cost function. So Kalman filter least squares is very similar to generalized forgetting, but with slight modifications. So you'll notice in the loss term, we're transitioning state X from step K plus 1 back in time to step I plus 1. In our forgetting term, we're transitioning from step K plus 1 back to step I. And then in the regularization term, we're transitioning from step K plus 1 back to time 0. And if we minimize this cost function, we get the following recursive update equations, which look very similar to the Kalman filter update equations, although not exactly the same. And this gives us the key step in relating RLS extensions and the Kalman filter. So using Kalman filter least squares, if we chose this special choice of process noise, then we would get from the Kalman filter to Kalman filter least squares. Or in reverse, if we chose this special choice of FK, then we would get from the Kalman filter least squares to the Kalman filter. Also, you can notice that generalized forgetting RLS is the special case of Kalman filter least squares with identity dynamics and no input. So putting that all together, we get that extensions of RLS are in fact special cases of the Kalman filter. Here are some examples from the literature. For example, exponential forgetting is Kalman filter with this process noise covariance, or different algorithms are special cases of the Kalman filter with this process noise covariance. So ultimately, all of these different RLS extensions are the Kalman filter with identity dynamics, no input, and some special choice of process noise covariance. Another cool thing you might notice is that the process noise covariance is often a function of PK, our covariance in RLS. So in other words, how much process noise you have is a measure, is like a function of how uncertain you currently are. Okay, and then maybe one last question is, how can we interpret this identity dynamics thing? Like RLS is the special case, the Kalman filter with identity dynamics, but why is that? Maybe one way to interpret that is the Kalman filter has two methods for identifying your state, which are a model of how the state changes and data you're collecting about the state. And you kind of balance these two out to figure out what is your current state. Whereas in RLS, you have no model of how your parameters are changing over time. You just believe that they do change. So you're entirely using your data. And maybe what's the default model? The default model is identity, that your parameters aren't changing. Okay, so inspired by this, we're going to try to develop a new class of adaptive Kalman filters inspired by RLS forgetting algorithms. Okay, so the trick here that we're going to use is modifying the Kalman filter to introduce a forgetting term. Here we're using the two-step Kalman filter update equations, so like the prediction step and the update step. And we're going to modify the prediction step to include two parts. The first is a forgetting part, in which we add PK plus sigma forgetting, where that forgetting is from various RLS extensions. And the second is the standard Kalman filter prediction step. And we'll show that this can improve state estimation in unmodeled disturbances, because in RLS, we have no model and forgetting is able to overcome that. Maybe the intuition is that we can use forgetting in the Kalman filter to compensate for things that are unmodeled. So here's an example of a spring mass damper with elastic collisions. And our Kalman filter is going to be given the nominal model of the spring mass damper, but without any collisions. So it thinks it's like a normal spring mass damper, but in reality, it's bouncing off of this wall. So let's see what happens when we use regular Kalman filter. You'll see that KF1 is with large process noise covariance and KF2 is with small process noise covariance. So KF1 in blue is able to really quickly adapt when you hit the wall because it has very little trust in the model. So very quickly we're able to track when we hit the wall. However, in steady state, we have really little trust in the model, so we're really noisy because there's some noise in our measurements. Green, on the other hand, is much more trusting of the model. So we have a much slower response when we hit the wall. But in steady state, things are a lot smoother. We are able to reject the noise because we are trusting our model. Our adaptive Kalman filter is trying to do kind of both. So we're using an adaptive Kalman filter with an extension of RLS from the literature using variable rate forgetting factor. And so you can see this in the bottom, which is our lambda. Lambda equals 1 means we have no forgetting. And when lambda becomes smaller, then we're forgetting. So we're trusting our data more than we're trusting our model. And you'll notice that every time we hit the wall, our lambda decreases. So we trust our model less and we trust our data more. And we're kind of alternating between trusting our model and trusting our data. And what this allows us to do is faster tracking of our state when we hit the wall. But then in steady state, we're less susceptible to noise. And so in this example, we are measuring the position. So YK is the position of our spring mass damper, and we're estimating both our position and our velocity. Okay, and so maybe to think about why this happens, you'll see that in KF1, we have really large process noise covariance, and in green KF2, we have very small process noise covariance. Whereas on our adaptive Kalman filter, we're kind of switching between the two. So we're switching between trusting the model, trusting the data, back and forth. And a really nice thing about this is that we're not modifying our RLS algorithm at all. So we're using it completely as is from the literature and plugging it into the Kalman filter. And it's like our adaptive Kalman filtering framework that allows us to do that. Okay, that concludes the technical portion of my talk. And I'd like to give some acknowledgements. First is my funding. I was very generously funded by National Science Foundation, the Graduate Research Fellowship. This funded pretty much the entirety of the last 3 years of my PhD and gave me tremendous freedom to decide my research direction. So I'm really grateful for that. The second, I'd like to thank my committee for their support and all their great feedback. In particular, I'd like to thank my advisor, Professor Bernstein. I think Professor Bernstein has been a really great advisor for me for the past 5 years. He's given me guidance when I need it and also given me freedom to really explore when I needed it. And he's always the guy that gives me that push to keep going, gives me that encouragement. So I really appreciate that. The next are my lab mates here, some past and some new lab mates. I'm really grateful for your collaborations and for your mentorship and all of your discussions over the past many years. You guys really make the PhD experience what it is. In particular, I'd like to thank Asim in the top left. Asim was a really big mentor for me in my first year in the PhD. He really got me going on so many things and got me started in a lot of hurdles. And I really would like to thank Asim for helping me. Some additional acknowledgements. I wanted to talk about two really important mentors for me from my undergrad. First was Dean Antoine, who was kind of the dean of my undergrad engineering program. And he was a huge part of my professional and personal development and got me here in many ways. The second is Professor Berlione, who is my undergraduate advisor. He's kind of the guy who introduced me to controls research, first taught me how to write a research paper or like a fellowship application. So I have him to thank a lot for getting me to here. I'd also like to thank AFRL, particularly Scott Nivison, who was my mentor there for a great internship, and for a really great internship at Reliable Robotics. I'd like to thank my friends that I've made here in Ann Arbor and from the past. I think you guys have always been there to support me, and I'm really, really grateful for you guys. I'd like to thank my family, both my parents, my sister, and also Laura's family that's kind of taken me in and given me that support. And I'd like to thank my wife, Laura. I made this little montage. Yeah, this montage kind of broke my PowerPoint. It's a little too big. But yeah, we've been together like 8.5 years now, and you've been there for so many moments to support me. Yeah. I don't know how long this ago, actually. So yeah, thank you, Laura, for really being there to support me the whole way. And with that, thank you for listening, and I'll take any questions.
That must be difficult. Any questions from the audience? Not faculty, audience.
Jeremy.
Oh, yeah.
That was a really great presentation. I was curious about the adaptive Kalman filtering. Do you have any kind of estimation or guarantee on like the convergence when that event happens that causes it to start forgetting?
Yeah, that's a great question. Sorry, let me skip through this. Yeah, so what's really nice is you can use algorithms directly from the literature. One thing I didn't touch upon is how this algorithm actually works, since it's not my algorithm. The way it kind of works is if the error you're seeing is bigger than normal, you believe that your system dynamics are not behaving nominally, so then you'll forget more. In terms of guarantees, there really aren't a lot of guarantees because they're based on the data you're collecting. But yeah, that's kind of how it works in practice.
Curious about your, like on slide 45, where you have like the cost function for the generalized Kalman filter. Because of the minus, does it make it non-convex, and does that cause any problems with how things work?
Oh, great question. Yeah, so there is a kind of technical condition that I didn't include in there, which guarantees that your cost function has a unique global minimizer.
That's assumption 2 then. On the next slide.
It's actually, I didn't put it here, but it's some like assumption on your FK.
Okay.
But in practice, it doesn't really hinder any of the extensions from the literature. Like all the extensions from the literature still satisfy the condition. Yeah. Yeah.
In the beginning, you showed the cycling resetting. Where you said it brought down the complexity from n cubed to pn squared. I probably missed when you defined the dimensions. So I was wondering, is it really worth having this reduction, given that you introduce oscillations in your parameters, and these might actually then propagate through what you're doing with the parameters? I mean, you're not estimating parameters for the sake of estimation, but you actually want to feed them typically back to somewhere, and if you have oscillations introducing the system, that might not necessarily be very, very nice. So, could you maybe just remind me what those dimensions were, and if it really has practical impact to have the reduction in the
Definitely. Yeah, that's a really great question. Is it worth it? That's a good question. I think the answer is sometimes. Yeah. Yeah. Okay, so the complexity is lower. You don't have to directly invert an n by n matrix. So instead of n cubed complexity, your p n squared complexity, where p is your number of measurements per step. Often p is like 1, so you're saying like n cubed versus n squared.
And n is the
number of parameters. Yeah.
You might want to remind people what P is.
P is your number of measurements per step. Yeah.
Per cycle of resetting, or per?
Per each step.
Okay.
Yeah. Now,
One means one sensor, like one, I don't know, rate channel.
Yeah. The question, is it worth it? So the oscillations are not in the parameters. The oscillations are in the covariance. So like if you look at the top, you'll see that the covariance is oscillating, but your parameters themselves are not oscillating. So if you look at the bottom, theta 3, yeah, you have like some oscillations in how confident you are, but in terms of actual performance of the algorithm, it is often like very similar. So you see like yellow performs really similarly to red. Now, this is kind of because this is low dimension, like this is only dimension 4. If n were very large, these oscillations would get much bigger, in which case it probably would not be worth it anymore. Another question is like in many adaptive control algorithms, RLS is not the bottleneck. You have some other bottleneck.
Yeah.
So it might be okay just to take the n cubed complexity.
Yeah, thanks.
Yeah. Yeah.
Any other questions?
Can I ask a question?
Yeah.
Someone speaking.
Oh, yeah. Hi, this is Jeremy. Nice talk, Brian. Can you hear me?
Yeah. Hey, thanks, sir.
Oh, yeah. So I'm just curious how the performance of this algorithm would change based on like you have the true theta as like a sinusoidal and cosine functions, right? They're really well behaved.
Mhm.
If they have, you know, over time, if the frequency changes to like higher frequency of oscillation, or if the function is not well behaved, like I don't know, maybe a sudden knock on a bird or something like that, it just have it flying somewhere else. How does the algorithm account for those? I guess you kind of covered it with the not the pendulum, it's the block on a spring example.
Yeah.
Yeah, I'm just curious how that would change.
Yeah, that's a great question. In RLS, the forgetting factor lambda, like tuning this tunes how quickly your algorithm can learn. So like how quickly you can change your parameters. I guess it doesn't really matter how your true parameters are varying. They could be like a sine or like a step function or like a ramp or whatever. The thing that matters is how quickly they're changing. If your true parameters were changing too quickly, then eventually you wouldn't be able to keep up. But so long as they're changing not too quickly, no matter like what kind of function it is, you should be able to track them.
Okay. I mean, like if you vary p, I suppose, the number of measurements, would that account for a lot of the frequent changes in status? I know that
Not
that
sure.
might be a little bit too computationally heavy for computers to follow, but theoretically speaking, would that be an easy way to fix it, or do you think there's a different way?
Changing the p number of measurements.
If so, let's say like you have theta true as a sinusoidal wave that goes in higher frequency as time passes. Then you said your last answer said that it's like it changes too fast, so the algorithm cannot keep up, right?
Yeah.
So one way to get around that would it be to increase the number of measurements?
Good question. It would definitely help. Although in practice, the number of measurements per step is kind of fixed by your setup, like how many sensors you have.
Okay, gotcha.
But yeah, it would definitely help. You have a ton of sensors.
Gotcha. All right, cool. Thank you.
Did you have a question?
No, we're good. I'm good.
All right, there aren't any other questions from the audience. Let's thank Brian again.